Hello, future engineers, subscribers, viewers, and students. Here is another video about cables under point loads. And in this video, I present two ways. One is the static approach, the basic static approach, and the second one is applying the general cable theorem. So here is the problem. The cable carrying three 400-pound loads has a sag at C of 8 sub c equals 14 feet. So this is 14 feet, the distance from the point of the cable to the imaginary cord. It happens here that the supports are on the same level. So the sag or the distance from the point to the imaginary cord is the vertical distance from the point of the cable to that imaginary cord. Take note that there are cables where the supports are not at the same level, and we can still apply the general cable theorem as well as the equation of statics here, basic equations of statics. So let's denote this as HB, sag at B, HD at D. Then, because the loads are vertical, the horizontal component of tension should be the same at the supports. If we're going to prove that, you just sum up forces horizontal. So rightward force should be equal to leftward force. I denote the vertical component of tension at A as VA and the vertical component of tension at E as V sub E. The tension in AB therefore is square root of H square plus V sub A square. And the angle that this cable makes with horizontal is inverse tangent of HB over 8. So in general, when the loads are vertical or projected upon the horizontal, if the tension in the cable is T and it makes an angle of theta with the horizontal, then these are the components of tension. The horizontal component of tension, which is constant in this case at any point on the segment of the cable, and the vertical component is is denoted by V. So tension is either square root of H square plus V square, or from this fact that tension is that the horizontal component of tension is T cosine theta, so the tension is horizontal component of tension, which is constant over cosine theta for this type of cable. So, so tension is H over cosine of theta. So I now present the static approach, summation of moments about V equals 0, clockwise positive, so we have VA times 40 feet, that's 40, is equal to 400 times 12 plus 400 times 24, then plus 400 times 32. So VA therefore is 680 pounds. Likewise, summation of moments about A equals 0, counterclockwise positive, so V sub E times 40 equals 400 times 8 plus 400 times 16 plus 400 times 28. So V sub E is 520 pounds. To solve for the horizontal component of tension, we cut the portion cable CD and we consider the forces to the left. You can also consider forces to the right. The result in solving for H should be the same. So summation of moments about C, considering the forces at the left of this section. So we have H times 14 feet plus 400 times 8, then equals V sub A, which is 680 times 16 at this point. So H is 548.57 pounds. We can then solve for the tension in AB, square root of H squared plus VA square. So VH 548.57 square plus vertical component of tension 680 square, so 873.7 pounds. By the way, the maximum tension occurs where the slope or the angle that the tension makes with the horizontal is greatest. So that cosine of that angle is smallest because t is h over cosine of theta. T would be maximum if cosine theta is minimum, and that happens when theta is maximum. So it occurs in AB because the angle here is greatest. If we consider that this is correctly drawn or drawn to scale. But anyway, it's also the maximum tension. For BC, we need to solve theta BC, and to solve for the angle BC, we need HB. So since we already computed H and VA, we have by similar triangle, HB as to 8 feet equals VA 680 as to H, which is 548.57. So HB is 9.917 feet. Therefore, tangent of theta BC is 14 feet minus HB 9.917 divided by 8. So theta BC is 27.04 degrees. The tension in BC therefore is H 548.57 over cosine of 27.04, and that is 615.9 pounds. Likewise, to solve for HD by similar triangles, this triangle here, HD as to 12 equals vertical component of tension 520 as the horizontal component of tension 548.57. So HD is 11.375 feet. Tangent of theta CD therefore is 14 feet minus HD 11.375 all over 12. So theta CD is 12.339 degrees. So tension in CD is H 548.57 over cosine of 12.339 degrees. So tension CD is 561.5 pounds. Finally, the tension in DE, since we already obtained H and VE, square root of H square 548.57 square plus 520 square. So 755.9 pounds. Now, that's it for that part if you want to present the solution in this manner. But I apply the general cable theorem because it is a good theorem also. So remember at, that is that theorem is applicable if the loads are projected upon the horizontal or if the loads are vertical. So we draw a beam, simply supported beam, and we apply the loads, same loads at the same locations, same distance also. So we sum up moments about the right side. So R1 times 40 equals 400 times 12 plus 400 times 24 plus 400 times 32. So R1 is 680 pounds. So likewise, if you sum up moments about 1 equals 0, you'll get R2 equals 520 pounds. So R2 times 40 equals 400 times 8 plus 400 times 16 plus 400 times 28. You'll get 520. So this is the general cable theorem that the product of the horizontal component of tension and the distance of the point on the cable to the imaginary cord, in this case because it is HC that is known at the start given. So H times 14 feet is equal to the moment at the same point on the beam with the same loading. So this is point C, moment at this point also at C. So considering from the left to that point, this is the positive sense of moment at C. So moment at C is 680 times 16, then minus 400 times 8. So that's it. Moment at C also, if you consider the forces at the right, is 520 times 24 minus 400 times 12. So it's the same as that. So solving for H is 548.57 pounds. Likewise, to solve for HB, we use the general cable theorem because we already know H, which is 548.57 by statics, and this is by the general cable theorem. So by general cable theorem again, 548.57, the product of the horizontal component of tension times HB equals the moment at B. which is the moment at B considering the left segment is simply 680 times 8. So solving for HB is 9.917 feet, the same as this value by similar triangles from here. Then finally, HD, I'll solve HD into two ways. Moment at D, considering forces at the left. So H times HD is the moment at D, and the moment at D considering the forces at the left segment would be 680 times 28 minus 400 times 20 minus 400 times 12. So solving for HD, it is 11.375 feet, which is the same as that. Another way of solving for HD is considering the right segment. This is moment at D, which is H times HD equals 520 times 12. And you will get the same 11.375 feet. So that's it for this video. I hope that you learned, aside from the so many example problems on cables that I uploaded in YouTube and in Diggler.